So now in this video we're going to look at a circuit that I put together that a long time ago that I really like. I'm going to try to keep it brief though. It covers a bunch of fragments that I covered in earlier videos. We have a reference voltage, percentage of the supply voltage. We have a signal voltage. Usually it is a percentage of the supply voltage, but I modified this so that we have a fixed lower amount of voltage that we can work with in relationship to the supply voltage. So we can adjust it, but once we adjust it, it'll be fixed whether the supply voltage changes or not. So we have a couple topics there covered in recent videos. And then of course we have the output in this case, that either sinks or sources current. We're using kind of high voltage, so I got kind of higher value resistors. So all stuff I covered before. Now let's get to the actual demonstration. So I didn't mention it in the title, but there'll be something related. And if I bump the power supply, it kind of cuts power. I should really add a large value capacitor to the rail. But in any case, what we have, it could be used as a low voltage cutoff. In this case, I just want to say, hey, your voltage is too low or whatever, with the red LED right there. So I have it set to 10 volts. And, so if I keep going lower, it's going to stay red, no matter how much lower I get. And then, as long as we got enough power to power the circuit so that it can do all the stuff it's got to do. And if I go enough above 10 volts, 10.1 is enough. I can get this to a tenth of a volt pretty easy. I can keep going as high as I want. I can go up to 15 volts, even 15.5 is probably okay. I didn't mean to go to 16.5. But in any case, these are, somewhat higher value components. So we're probably okay even at 16, but I'm going to limit it to 15. So, in any case, the main takeaway though was that when the voltage gets to a certain point, output's going to go high right there, giving us a red LED. And I kind of had the lamp dimmed. I can see the red LED in person really well, but it's not showing up on camera terribly well. So, what if we don't want 10? Let's go down first. 9. Very simple. We got it red. We are going to turn the trim pot, so if I keep going up, it's going to stay red. Turn it down till it turns green, and since it's 9 that I want to be, I'm just going to inch up this trim pot to until it turns red right there. So that's right at the spot. And if I did a good job, 9.1 volts, we should have green. And again, we can do the same thing with at 11 volts in the opposite direction. Right there. Although there will be a limit to 11 volts is probably as low as I can go because I have a fraction of a voltage at the trim pot. But in any case, there we go. We got red at 11.1. Going to inch down until it turns green. And so now we got green. If I go slightly lower than 11.1, I'm bumping the power supply. So it's interrupting power. There you can see it's red. And again, if we would rather set it when we're at the one where we want it to be red, indicator that we're as low as we want to go. If we got a battery we're discharging or something. Again, get it green and then turn the trim pot until right when it turns red right there. And so that's just the way it goes. If you have a certain spot where you want it to flip, you just make the adjustment until you get right to the point where you get the flip that you desire. So now the secret to this circuit is the op amp here wired as a comparator. So we have a reference voltage of half of the supply voltage right there. So our limitations could be improved with a different value Zener diode right here. But this is what I have. I made this a long time ago, probably for a good reason. But in any case, again, 11 volts is probably where I would want to shut off a circuit with a lithium iron phosphate battery. So I think we're probably okay here. We're getting half of the supply voltage right there. So if it's 7 volts, then this point right here would be 3.5 volts. If we get the supply voltage to 10 volts, this would be 5 volts. So this one slides up and down as the supply voltage changes. So that's what we want to respond to. And so we have over here, the reason why it's fixed, we have a Zener diode right there. So we're going to get about 5.6 volts across this trim pot right there. It shuffles slightly with voltage changes. ideally we would have high value resistor coming from the output to the non-inverting input there to kind of help raise and lower the voltage in the direction that the output is. That would help stabilize things a little bit. But for the demonstration circuit, we're going to keep it simple. So in any case, it fixes the voltage across the trim pot right there. And then you can go up and down between 0 volts up to 5.6 volts. And generally speaking, when you raise the supply voltage, the higher the supply voltage, more current's going to go through that resistor, but then more current's going to go through the Zener diode. That's the way it works. Whatever extra current you got when you hit 5.6 volts, just going to go right to ground through the Zener diode. They're made to conduct current well reverse bias. And while they're conducting current, their Zener voltage is going to build up. If you're using a 5.6 volt Zener diode, it's going to be relatively steady. We looked at that in the last video. It changes slightly as the supply voltage goes up so that more current goes through, but not a ton. And so it should work okay here. You can use actual reference voltage integrated circuits like the 7805. There's 7810 as well if you want 10 volts and so on, which actually might be better if for the use that I want to use. But in this case, we're just going to limit it to about 11 volts where we want the output to change. So we got half that supply voltage. This is to the inverting input right there, which means that when you got more than half of the supply voltage to the non-inverting input, so the voltage is high enough, then the output is going to be high. And you got red right there. If you get lower than half of the supply voltage at the non-inverting input, then the output is going to be low. It's going to connect ground as good as it can. Since we're using 5 volts, I'm protecting the LEDs with 2,200 ohm resistors, 2.2K. And if you look at the packaging, it says 2K2 because they take the omega symbol, well, the K. They take the K symbol for kilo. That's what I should have said. And they shuffle it over to where the decimal point would be, because you might not see the decimal point. As you can see there, that might look like 22 if I'm far away enough or something, but you can definitely tell that's 2K2. So in any case, since we're working with 5 volts, we're protecting the LEDs with that. Again, topics we covered a lot later on. So let's get to the 10 volt point. If we have 10 volts at the supply, that's going to give us 5 volts at the inverting input. And so we want the output to be read at 10 volts or less. So we got 5 volts right there. If we set 5 volts at this point right there, then that means if we get this any lower, then this will be higher, which means the output will be high. Red LED lights up. So this is too low, output's high, red LEDs light up. So again, we got 5 volts here. We go above 10 volts, we'll have more than 5 volts at the inverting input right there, because it's half. So more than 10, more than 5. This is higher. The output wants to be more like this one. Since this one's higher, that one's lower. It's 5 volts, which is lower than the above 5 volts, and thus the output is low. We got the blue LED. So as this goes up, it's higher, but since we have the opposite, it's going to be low, and that'll be good, no matter how much higher we go. And the same with going lower. We get this lower than what we set here. Again, it's going to be half the supply voltage, because these inputs are not too good getting, comparing when you get close to the full positive voltage or all the way down to no voltage ground right there. Does a much better job comparing the two voltages when they're kind of in a middle range right there. So, in any case, hopefully that makes sense. Hopefully you can just look at this schematic and understand what it's doing. But I thought I would explain that as well. Okay, it looks like I put a note. I made this a long time ago, and I didn't really review the notes. But yeah, it looks like you can work with 7 volts to 11.2 volts with this particular setup. You could use a larger Zener diode, and you could still go down the same amount. But with the higher voltage Zener diode, you could work with a higher supply voltage where you want it to cut off at. And So I just did this demonstration for whatever reason in the past. Apparently 11.2 was my goal for the minimum voltage of a battery, probably. Lithium iron phosphate batteries again. Kind of want to stop using them at 12 volts, but you can still use them a bit. You definitely don't want to go below 10 volts. So 11 volts would be a really nice safety spot to actually like cut it off. There's not much more powerful available in the battery anymore, and dropping below 10 can be dangerous. So might as well just say, hey, at 11, for whatever reason, when the output goes high, it's gonna disconnect the battery, turn off a relay or something, you know. So you could use that. That was probably my intentions when I designed this. So hope you enjoy. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.